Welcome. So, have you ever been working with NumPy, changed one array, and then to your complete surprise, a totally different array changed right along with it? Yeah, if that's ever happened to you, you are in exactly the right place. Today, we're going to demystify one of the most important and honestly most confusing concepts in NumPy, the difference between a view and a copy. Getting this right is absolutely key to writing clean, efficient, and bug-free code. So, let's dive in.
All right, here's our game plan. We're going to start with what a NumPy array actually is under the hood. Then we'll get into the two main ways of indexing and see how one creates views and the other creates copies. After that, we'll check out some really powerful tools for multidimensional arrays, see how to mix and match these methods, and then finally, we'll wrap it all up by talking about what this means for your day-to-day coding.
Okay, before we even write a single line of indexing code, we've got to understand the structure of a NumPy array. You know, it's not just a simple grid of numbers. There's a specific anatomy to it, and that internal structure is exactly what makes it so incredibly fast and powerful.
At its heart, every single NumPy array is really a two-part system. On one hand, you have the data buffer. Just think of this as one big, long, continuous chunk of memory that holds all your raw numbers. It's like a block of stone. Then, on the other hand, you have the metadata. This is all the information about that data, things like its shape, the data type, and something called strides, which tells NumPy how many bytes to jump to get to the next element in a row or column. The metadata is like a stencil you place over that block of stone. This separation is the key, and I mean the key to understanding everything else we're about to talk about.
So now that we have that two-part structure in our heads, the data and the instructions, let's look at the most common way we access that data, basic slicing. This is where we run into the idea of a view, and you're about to see how it's a direct consequence of that anatomy we just discussed.
So what in the world is a view?
Well, when you do a simple slice on a NumPy array, NumPy does something incredibly efficient. Instead of wasting time and memory by creating a whole new array with all the data copied over, it just creates a new, lightweight array object with slightly different metadata that simply points to the exact same data buffer as the original. It's like having a new window that looks at the same scenery.
Let's see this in code. It makes it really clear. First, we create a simple array, x, with the numbers 0 through 9. Then we create a new array, y, by taking a basic slice of x, everything from index 1 up to, but not including, index 3. Now, because this is a basic slice, NumPy creates a view. Y looks like it holds the numbers 1 and 2, but the critical thing to remember is it's not holding them. It's just looking at them inside of x.
Okay, so this brings us to the most important question of all. Since y is just a different window into the data that lives in x, what do you think is going to happen if we reach back into x and change the very numbers that y is looking at?
And there it is. We go back and change the elements at index 1 and 2 in our original array x, and when we check y again, it's changed too. This is the punchline. They are two different Python objects, but they are both looking at the exact same block of memory. This is fantastic for performance, but as you can imagine, it can lead to some really sneaky bugs if you're not paying attention.
So, now let's flip the coin. If basic slicing gives us this super fast but potentially dangerous view, how do we get a completely separate, safe, independent version of our data? Well, that's where a different type of indexing comes into play. We call this advanced or fancy indexing. The idea is simple. Instead of a simple start-stop slice, you give it a list or another array of the exact integer indices you want to grab. So you can pick out, say, the second, seventh, and fifth elements in that order. It's incredibly flexible. And the most important rule here is that this operation always creates a copy. A copy is exactly what it sounds like. It's a brand new array. NumPy sets aside a new block of memory, creates a new data buffer, literally copies the values from the original over to the new one, and then creates a new set of metadata for it. Sure, it's a bit slower and uses more memory, but the huge upside is total data isolation. Let's look at the code. We start with our same x array. But this time, look at how we create y. We're passing a list of indices inside the brackets. 1, 2, 8. That list is the trigger for fancy indexing. As a result, y is now a completely new array, a copy, that contains just the elements from those specific positions. And now for the big reveal. We do the same thing as before. We go back to x, and we change the values at those same indices we just selected. But this time, when we look at y, it's completely unchanged. It still has the original values of 1, 2, and 8.
because y is a copy. It's living in its own world with its own data, totally safe from any changes we make back in x.
Okay, so we've nailed the core difference between views and copies. Now, let's level up and look at some of the really slick tools NumPy gives us for working with multidimensional data. First up is the ellipsis, which is these 3 dots. And honestly, this is a real lifesaver. Imagine you have a 4D array and you want to grab all the elements along the last dimension. Instead of typing out colon, comma, colon, comma, colon, comma, you can just use the ellipsis. It's a shorthand that basically means, hey, NumPy, just fill in as many full slices as you need right here. It makes your code so much cleaner. Next, we have np.newAxis. This one is a bit more of a conceptual tool, but it's incredibly useful for reshaping arrays on the fly. It doesn't actually add any new data, it just injects a new dimension of size 1. Now, why would you do that? Well, it's essential for something called broadcasting, which is NumPy's magic for performing math on arrays that have different shapes, like adding a vector to every column of the matrix. np.newAxis helps you line up the dimensions so that can happen.
Okay, let's talk about a super common problem. You have a 2D array, a matrix, and you want to pull out a subgrid made of, say, the first and fourth rows and the first and third columns. Your first instinct might be to just pass 2 lists. But if you do that, NumPy pairs them up and gives you back just 2 values, a of 0, 0 and a of 3, 2. That's not the grid we wanted, so how do we get the whole thing?
The answer is a special helper function called np.ix_. This thing is designed specifically for this problem. You feed it your lists of row indices and column indices, and it constructs the necessary index arrays behind the scenes to select the full cross product, that is, the complete rectangular grid defined by your selections. As you can see in the code, it works perfectly, giving us that 2x2 subgrid we were after.
Now, where NumPy indexing gets really interesting is when you start to combine these different techniques, basic slicing and fancy indexing, in a single expression.
Let's break down this example because NumPy actually processes it in stages. First, it looks at the row index, 1 colon. That's a basic slice, so it creates a temporary view of all the rows from the second one to the end. Then it applies the fancy index, the list, 201, to the columns of that temporary view. This selects and reorders the columns. Now, here's the key. Because the final step in the chain was fancy indexing, the final result you get back is a copy, not a view.
Whew, okay. We have covered a ton of ground, from the deep down anatomy of an array all the way up to these complex selection methods. So let's bring it all home and focus on what this means in practice, for you, writing code.
This table really sums up the central trade-off perfectly. On one side, you have views, which you get from basic slicing. They are incredibly fast and use almost no extra memory, but they carry that risk of accidentally changing your original data. On the other side, you have copies, from fancy indexing. They are completely safe and isolated, but that safety comes at the cost of performance and memory.
So, the most important takeaway is just to be deliberate. Know what you're doing. The rule of thumb is simple. Slicing gives you views. Indexing, with lists or Boolean arrays, gives you copies. If you ever find yourself with a view but you need a safe, separate copy to work on, just call the .copy method on it. It's really about choosing the right tool for the job. Choose views when you need speed and you're just reading data, and choose copies when you need safety because you're going to be modifying it. And I'll leave you with this final thought to chew on. Now that you know this distinction, how does it change the way you might approach debugging? So many of those really weird, hard-to-track-down bugs in data analysis pipelines come from this exact issue. A function accidentally modifying an array that was supposed to be a safe local variable, but was secretly a view into your main dataset. By always asking yourself, am I working with a view or a copy, you're going to start writing much more predictable, robust, and ultimately much better code.